Okay, folks, this is lecture 24. Uh, it's actually the last new stuff for the course, which happens to be set up in hold times, and not a big topic, but then again, massively important in digital circuits. Okay, so let's do this thing. Let's find a thing. Okay. Okay, so, we've talked about this before. Essentially, it has to do with frequency and period, and the relationship between frequency and period is a reciprocal relationship. Frequency has the units of seconds, or seconds to the -1 or time to the -1. Frequency also uses the metric of hertz. Okay, so 1 over, I guess hertz is equivalent to seconds raised to the -1 power. Okay, but once you flip that seconds to -1 over, it becomes seconds, which is time, which is the period. Okay, so once again, when you're talking about period, it's a time measurement. When you're talking about frequency, generally speaking, it's a frequency measurement. Okay. Okay, so in digital electronics, there's two extremely important times, particularly when you're working with synchronous circuit here. You can't drive a synchronous circuit with a super fast, amazingly fast clock cycle. Once you do that, at some point, as you increase your frequency, generally speaking, they call it a system clock frequency. As you increase that frequency, at some point your circuit's going to break down, and generally not break down, it's just going to quit working properly. And generally what happens is that it's going to violate a setup or hold time. So these devices we're working with, they're synchronous, which means their operations are synchronized with the clock edge, which sounds good and easy and straightforward and all that, but the issue is there's some issues with it. Okay, namely, there's a setup and a hold time. So you have that clock edge happening for that device where all the inputs are synchronized to. What happens is sometimes before that clock edge, whether it be a rising or falling clock edge, you have to hold all the other inputs stable. And sometime after that clock edge, those inputs need to be kept stable for a while. So the amount of time before that clock edge that you have to keep those inputs stable is referred to as the setup time. So this is the setup time, and the time that you have to hold those inputs steady after that clock edge is the hold time. So I'll put arrows there, make it look even worse. So the issue here is it's a physical thing. These are physical circuits. You got transistors transferring charge around, blah, blah, blah. I'm not going to pretend to know the specifics of this thing, but I do know that anytime you violate the setup and hold time, your circuit's not going to work. And it's not going to, it'll work, some of the time, the other times it will freak out. But the issue is that it's, you violate a setup and hold time, your circuit's going to be weird. And it's going to be a hard error to find. So I always tell people, you're going to be designing a circuit someday. You've designed a circuit, it's acting weird, you can't figure it out, and suddenly it's going to hit you. You violated a setup or hold time. You're going to fix it, and your circuit's going to magically work. Mark my words, it's going to happen to at least some people, particularly if you become a digital designer. The issue in this class is it's hard. It's a really important topic, but it's hard to devise an experiment where it kind of like sheds light on the topic, and so we really don't do it. But what I choose to do instead, and I think it's the only thing I think of doing, is using these in a problem. Okay, so what I want to try to do here is find, these are typical, up here is just a typical simple state machine circuit as I used to draw them. We don't really draw them that way anymore, because generally speaking, this is considered the output decoder, this is the input decoder, and these are the state state register. So we've been kind of bumped that up to actual decoders, and we don't really look at this anymore. But it doesn't matter. Underneath input decoder and output, so the next state decoder, input decoder, there's logic. Logic has propagation delays. Once again, this book doesn't really cover them that much. All devices have propagation delays. That means it takes a finite amount of time for that signal to go through the device. Okay, so if everything has a finite amount of time, and then you have these registers here that have setup and hold times, obviously at some point when you're raising the clock frequency of the circuit's going to stop working properly. So what we want to do is look at just this type of circuit and the problems we're going to deal with. Even more specifically, we're not going to even look at the output decoder. We're just going to look at the state registers and the next state decoder. Now we should be looking at the output decoder more properly, but we don't. And simply because it makes the problems more complicated. And once again, we don't really have any real-world examples on this, so I don't like doing it theoretical. So I just kind of simplify these problems down. So anyway, what I'm trying to do is find this minimum clock period, which is the same thing as the maximum clock frequency for this circuit. So I have a couple things going on here. I'm looking for 4 different values that I'm going to minimize here. So here's the setup time. Here's the propagation delay time through the circuit, to the state registers, or I call them the flip-flops in this case. There's also a propagation delay time through the next state decoder. And lastly, there's I call it a slop, which is simply adding a little bit extra time as a safety margin in this thing. Okay, so to simplify these problems, I state directly that this propagation delay time is longer than the hold time. So that means even for these problems, all we're interested in is the setup time, because the propagation delay time of the state registers is greater than the hold time, so we don't even have to consider the hold time. So once again, there's 4 values we need to consider in any circuit. We're going to add those up. That's going to give us our minimum clock period, which we could invert, and that's going to give us the maximum frequency. So let's do a problem here. Okay, well there's my it's the same timing diagram. What I want to do is add up these 4 values and invert it. That's going to be my maximum frequency. So let's do this problem here. All I have to do is read through this thing very carefully, dig out these 4 values, and what I'm going to say here is assume the propagation delay for the flip-flops is greater than the hold time. Okay, that means I don't have to consider the hold time. Assume the X input is stable and the Z1 outputs drive a circuit that are essentially not sensitive to the maximum clock frequency. That gives me the excuse of not considering the output decoder and not considering changes in X. Okay, so I'm really kind of simplifying these problems down. What you have to do is read through this problem to fill out this math, and then essentially that's it. Okay, so let's do this thing. I'm going to look through this thing. Flip-flops have a setup time. T setup equals 10 nanoseconds. And a propagation delay of 17 nanoseconds. T of the flip-flops equals 17 nanoseconds. Okay, next state decoder has a propagation delay of 13 nanoseconds. Next state DCDR equals 13 nanoseconds. And safety margin of 12 nanoseconds. Okay, I found them all. What I need to do is add these up. So that's into this equation here. I don't want to rewrite this. I'm just going to add it by hand. 10 plus 17, 27, 37, 40, 52. So T min equals, this is the minimum period, equals 52 nanoseconds. So F max equals 1 over 52 times 10 to the minus 9 seconds. and I'm going to leave the answer like that. So you can do the math on this, or you can not do the math on it. It doesn't matter. And that's it. Okay. Problem of the day is this example problem here that I want to do this example problem. And this turned out to be an amazing example problem. There's a lot going on in it. I called it a 10th grade problem, but actually it turns out it was a little bit harder than what I put on an exam. Okay, but the issue is if you could do this problem, you could do any exam problem. Okay, so this is a circuit that is essentially it's adding. I might as well draw the top level diagram on this thing. CKT. It has a clock. Someone presses a go button and something happens. It has an input value and it has a average. So what this problem is doing is it's essentially adding up numbers and taking the average of them. So it's really cleverly done in that. The problem is clever in that I'm adding 8 values, and to take the average, of course, I divide it by 8, which is a really handy number because I have a device called a shift register that does a great job of dividing by 8. Essentially, what I'm going to do is shift it right. Okay, shift it right 3 times. So that's my divide by 8. Okay, looks good. It's averaging, it's taking the average of 8 numbers, which means got to add those 8 numbers together, which should call out for an accumulator. Okay, so this problem has an accumulator and a shift register, but check it out. If you think about it, I'm going to be accumulating with the shift register. When I'm done accumulating those 8 values, I am going to essentially shift that shift register. So the notion with this problem is I could use a shift register as the register in the accumulator. And I think, God, maybe I want to draw that. No, I'm not ready to draw it yet. Okay, so the other issue in this problem is I need to do something 8 times. Wouldn't be too hard to do with 8 states, but that would be kind of clunky. What I need to do is just keep track of the things I'm doing, which is essentially an event counter, and which is in a counter. So essentially I'm going to have a counter in this problem that's going to be counting up. Okay, so when does it count up? It counts up every time I add a new value, from new input value to my running total, which is in the accumulator. Okay, one of the other issues in this problem is that I'm adding up 8 numbers, so that the problem doesn't specify the width of the output. It doesn't say anything about it being valid or not. The idea here is that I want the answer to be valid, so I want to make the width of the output big enough such that I can add together 8 8-bit numbers. So 8 8-bit numbers. So in the end, 8 is 2 to the 3rd times 2 to the 8th equals 2 to the 2. I got that wrong. 2 to the 11th, and this 11 here is going to be the width of my output. And if I'm doing numbers with 11 bits, that's not gonna ever be maxed out by the 8-bit inputs. Okay, so now one last thing in this problem. I'm not adding every number. I'm only adding the input value, if it's greater than 47. So obviously, somewhere in this problem, I have to check to see if the number is greater than 47, which calls out for a comparator. So in the end, I got an accumulator. It's going to be a shift register based accumulator, which comprises of a ripple carry adder and a shift register. I've got a counter. I've got a comparator, I have a state machine all as well. So we can, I think we're ready to write those down. So let's get rid of this, move that away, and let's start writing this thing. Okay, so this is going to be, this is going to be a shift register. This is my output. That's already wrong. I think we agreed it was 11 bits, which means I'm going to squish this down for the final version here, and there's my average right there. So the problem stated that it's an 8-bit output. I just need to do the internal math using 11 bits. Okay, there's my other part here. And remember, I'm not really putting a lot of thought into this yet because it's an accumulator. I've done this many times and I don't really have to think about it. Okay, looking good there. Some here. 11 bits. 11 bits. And this is the data. This is a clocked value. And this is my typical shift register with a select. Okay, let's fill that in. EL operation 00011011. These are the 4 possibilities of a select. Hold, load, shift right, shift left. Okay, that looks good. And by all means, I know this is something I'm accumulating, so I want to be able to clear this the shift register. Looking good. So I think I'm going to start drawing the state machine as I go along. Not the state machine. You know, the state machine, FSM. These are control inputs to the shift register. So I know they're going to be outputs of this state machine. So I'm going to do that as I go along. Clear. Okay, looking good. The thing that it potentially is going to be adding to this circuit is the input. There's my input, and looks good. I know I need a counter in this thing, so I'm going to put down a counter. CNTR. It's a clock circuit. It's a 3-bit counter. I don't really need the count output, but I know I'm going to count something. I know I need this RCO. RCO is going to be a status. Might as well put the go in there too. I know that's going to be a status. This state machine's clocked. Looking good. I need one more thing in here, which is the comparator. And what I need is to look at here is GT, and that's going to be a status. Here's your GT input. And what is it comparing? It's comparing a 8-bit 0x47 with the input value. We can just use the 8-bit value called A and B, which helps. And wow, am I done in this thing? Clear. And now I need to clear the counter to get it to non-state also. Okay, well, this is the other input. Okay, so I need to control whether I'm counting up on this thing. What I'm going to do is clear this. It's a 3-bit counter. It's going to generate the RCO when it hits 7, which means I'm kind of done with what I'm doing in the circuit. And so this is also a control input. And I believe at this point I think I've remembered everything. If not, I'll fill it in later. I do need to put a note here. Up equals 1 is an increment. equals 0 is a hold. Not clear exactly what hold's doing. I need to put a note there. And what else do I need in this thing? I would say clears. Clears are asynchronous. Good enough. I probably should put clears have a precedence over the other inputs, but that's usually a given. Okay, I think I got everything here. Once again, if I forget something, I'll just go put it in and change it as I need to. And so let's do this thing. Yeah, maybe there's a more structured way to do this, but I don't know what it is. Okay, so I am waiting for a go button. Okay, so as long as I'm waiting for a go button, what I want to do is make sure this output doesn't change. So I'm going to say SEL equals 0, 0. Okay, so I get a go. I get a go signal, and I am going to do some accumulation on this thing. Okay, in the meantime here, this output is doing its thing out there. So what I want to do is go not. Here's my go. That means when I get that go signal, the very first thing I want to do is clear stuff. Okay, which kind of begs the point of if I don't get a go input, I want to verify that I'm not clearing anything. And I think that looks good. So I'm going to look at this thing. For this particular state, I've covered the selects here. And I've covered a clear here, which is okay. That I really haven't put in the other select here because the clear has higher precedence, so I can go ahead and leave that out. So up is the same story. Up is kind of a don't care in these states. I don't need to put it in because it really doesn't matter what this counter is doing in this state. So once I get over into this state, you know, it's going to be a different story, but I'll worry about that when I get into that state. Okay. Adjust this seat here. Okay, so here I am in this state. I've got a couple things going on here. For sure, I don't want to be clearing the counter or the shift register. I believe I can turn both of these off. Both devices clear off and nothing will happen. Once again, if I'm wrong on that, I can fix it later. Okay, so in this state, you got a whole bunch of stuff going on. What's interesting here is in this state, I've got, you know, the go doesn't matter anymore, but the RCO and the GT are extremely important to me. And so those are two signals. There's two different, you know, it's two signals. They can both be 1 or 0. So I have 4 different cases. So I'm going to have 4 different arrows coming out of this state, which is okay. So I just have to make sure it's right. So let's do this. So the first thing we're going to look at is, let's look at the RCO not case. Okay, if RCO is off, I'm for sure going to stay in this state. But there's 2 cases of RCO not. There's the RCO not when GT is on, which means the input's greater than 47. So let's do that one. GT is on. Under those conditions, I haven't got a ripple carry out. Greater than is happening. What I need to do this thing is load the shift register. LCL equals 0, 1. Additionally, what else do I want to do to this thing is turn the counter up. Okay, so I want to increment the counter. Okay, so let's keep going on this thing here. Okay, RCO not, GT not. Okay, that means I haven't gone RCO, and it's not greater. The current value is not greater than 47, so I'm not going to add. So I'm I'm gonna look over here and steal this information. SEL equals, that means I want to hold it. I don't want to load this thing. I'm holding it because I don't want to add that new value. I don't want to do an accumulation, and by all means, I don't want to count up. Okay, and I think I'm done with that. Okay, so I need 2 more arrows, so I'm going to draw 1 right here. I think I'm going to draw it somewhere else. Draw a little bit lower. Okay, so this is the case where I'm done. Okay, that means RCO is turned on, it's greater than, and at that condition, I'm actually going to steal this information up here, equals 0, 1. I don't really care. I'm done after this point. I don't really care if I count up or not, so I'm just going to go ahead and leave up out of this particular transition because it's actually I don't care. Okay, so the issue is this final transition here is when, I think I'll put a note down here. Well, it's when RCO is on, but it doesn't get added. GT doesn't get added, or the input value is not greater than 47. So I stay in this state, and by all means, it's another hold. I'll put a slash there. 0, 0, and I'm not counting up. Okay, so there it is. There's my 4 arrows coming out of the state. So in this state, I don't know. I'm ready to divide this thing. Divide this thing by 8 for my average. I'll just say divide 1, and I know I'm not going to clear anything. This up is a don't care, so I'm just going to leave it out. I don't really care if it's counting or not. Okay. Oh, I need to turn the select here to divide by 2, which is a shift right, equals 1, 0. div2. Clear. I'm not clearing it. SEL equals 1, 0. Okay, right now my brain has disengaged. I am just writing this stuff down because it's the same stuff over and over again. I need to do 3 shift rights. Okay, so there's 1, 2, and 3, and by the time I'm done, the last shift right is going to happen when I leave this state, and it's unconditional, and I think I'm done with this problem. Look through this thing, see if I forgot anything. You know, up is a don't care here. You know, it doesn't really matter. I'm gonna clear it anyway. I could put it there, but it's don't care, so I'm gonna leave it out. And I'm just, you know what? I'm just gonna call this done. Okay, so once again, I'm waiting for a button press. I get a button press. I clear everything, and then I am adding 8 times if that value is greater than 47. When the last time it's greater than 47 could be indicated with RCO of the counter turned on. That's going to get me over to this state, which I'm going to, you know, do my final add, and then I got 3 states of shifting right, which is going to be my divide by 8, which gives me my average. Okay, folks, doesn't get any harder than this. Fun stuff. Talk to you later.